This is the screencast for section 8.2, example 7. Here's that little note again. Indeterminates infinity times 0 and infinity minus infinity can often be handled by using algebra to get a 0 over 0 or infinity over infinity situation where L'Hopital's rule helps us a lot. So in example 7, we're going to work with the indeterminate form infinity minus infinity this time. And we're going to find the limit as x approaches 1 of 1 over the natural log of x minus 1 over x minus 1. So first I'm going to see what happens as x approaches 1. Well, the limit as x approaches 1 of 1 over the natural log of x, well, as x approaches 1, I know the natural log of 1 is 0. So as we approach the y value 0 in the denominator, 1 is getting divided by a small and smaller and smaller value, so approaching infinity. Minus 1 over, and then again, 1 minus 1 is 0, so as the x values are approaching 1, we're getting very, very, very close to infinity. So we have an infinity minus infinity situation. That's our indeterminate form. So let's see if we can use a little bit of algebra to help us out in getting a 0 over 0 or infinity over infinity indeterminate form. Well, I think I want to find a common denominator. So I'm going to do that by multiplying the first term by x minus 1 over x minus 1 and the second term by natural log of x over natural log of x. And then that gives me the common denominator of the natural log of x times x minus 1. And in the numerator I have x minus 1 minus the natural log of x. So I'll plug in 1 and I get a 0 over 0 situation. 1 minus 1 is 0 minus the natural log of 1, which is also 0, so 0, over the natural log of 1, which is 0, times 1 minus 1, which is also 0. So there is my indeterminate form that tells me L'Hopital's rule might be a good idea. So I'm going to do that. I'm going to take the derivative of the numerator. So the derivative of x minus 1 is 1, minus the derivative of natural log of x is 1 over x. And then the denominator, I got to use the product rule. Derivative of natural log of x is 1 over x. The derivative of x minus 1 is 1, so put that in the product rule. I see these fractions inside fractions, so I'm going to just quickly multiply the whole numerator and denominator by x, which doesn't change the value at all, it just helps me simplify a little bit better. So I get the limit as x approaches 1 of x minus 1 over x minus 1 plus x natural log of x. Okay, so let's try plugging in 1. There's no more simplification from here. But if I plug in 1, 1 minus 1 is 0, over 1 minus 1, which is 0, plus the natural log of 1 is 0 times x, so 0 over 0. I got to use L'Hopital's again. So I'm going to take the derivative of the numerator, which is 1, and then the derivative of the denominator is 1 plus, well, derivative of negative 1 is 0. Then I'm going to use the product rule again, but now I get to simplify. Try plugging in 1. I have 1 over 1 plus 0 plus 1, so that's actually 1/2. The now try problem number 19 says identify the indeterminate form and evaluate the limit using L'Hopital's rule. Alright, so we have the limit as x approaches 0 from the right of cosecant of x minus cotangent of x plus cosine of x. So is that going to be infinity minus infinity? Well, there's 3 terms there. Hold on a second. Now, if x is approaching 0 from the right, we're talking about positive values. So that would be quadrant 1 on the unit circle. Cosecant is positive in quadrant 1, and there's a vertical asymptote at x equals 0. So that means we're going to be approaching positive infinity as x approaches 0 from the right for cosecant of x. Cotangent of x has a minus sign, but then also a positive value in quadrant 1 and a vertical asymptote, so we have another positive infinity. And then cosine of 0 is simply just 1. Well, we still have this indeterminate form, infinity minus infinity. Yes, there's a plus 1 after that, but that's determined. The indeterminate part is the infinity minus infinity. So let's see if we can do a little bit of algebra first. I'm going to try and find a common denominator and combine all these into one thing so I can start using L'Hopital's rule, derivative of numerator over derivative of denominator. So first, I'm going to take the limit as x approaches 0 from the right, and I'm going to write all these out in sines and cosines. And I can see that they all have a common denominator of sine, so this last term, cosine, I just multiplied by sine over sine to give it that common denominator. Now I can combine all that. So in the numerator I have 1 minus cosine of x plus cosine sine of x. And then in the denominator is just my sine of x. Now if I plug in 0, I have 1 minus the cosine of 0, which is 1, plus 1 times 0. So I have 0 in the numerator over 0 in the denominator. The sine of 0 is 0. So I have now a 0 over 0 indeterminate form, which I can use L'Hopital's rule on. Well, I'm going to take the derivative of the numerator. Let's see, 1 minus cosine of x. Derivative of 1 is 0. Derivative of negative cosine is sine of x. Plus, now I need the derivative of the product rule using cosine and sine. So there's that. And then the derivative of sine in the denominator is cosine. Alright, so let's simplify this mess. The limit as x approaches 0 from the right of sine of x minus, we've got a sine squared and then a plus cosine squared all over cosine of x. Well, negative sine squared plus cosine squared isn't 1, so I can't really simplify that. Let's just try plugging in 0. Sine of 0 is 0. Sine of 0, so minus another 0 then for sine squared of 0, and then plus 1 all over cosine of 0 is 1. So I get 1 over 1, which is 1. So the limit as x approaches 0 from the right of this function, the y values approach 1.